Hello everyone, my name is Suvrat Mehta and we'll be discussing today's Leetcode Biweekly. So let's start with the discussion. So first problem, minimum moves to equal array elements 3. You are given an integer array nums. In one move you may increase the value of any single element nums by I. Return the minimum total number of moves required so that all elements in nums become equal. So basically we are given an integer array nums, and the operation we can do is we can increase any value of any single elements of num by 1. What is the minimum number of moves so that all elements in nums become equal? So the test cases are 2, 1, 3. So obviously I will have to do +1 here and +1 here to make this 3, 3, 3. So that is 3 operations. And in 4, 4, 5, I will need to do a +1 here and a +1 here. So that will make it 5, 5, 5. That is 2 operations. So the thing is that we will be making every element equal to the maximum element. Because this operation is such that we cannot decrease a number. So basically we will not be able to decrease the maximum number, and as a result every number must be at least equal to the maximum number for all of these numbers to be equal. So why not just make them equal to the maximum number only? So we'll be making every element equal to the maximum element, and the time complexity required to do this would be simply O of n. We can find the maximum element in one iteration, and then we can just take difference of maximum element by every element and add that. So I'll show you guys the code. Maxval is the maximum element, so we will iterate over all the elements and find the maximum element, and then to calculate the answer we can just answer plus equal to maxval minus I and then return answer. So that was the problem A. If you guys have any doubts, you can ask, else let's move on to the problem B. Okay, so let's move on to the next problem. So count subarrays with majority element 1. You are given an integer array nums and an integer target. Return the number of subarrays of nums in which target is the majority element. The majority element of a subarray is the element that appears strictly more than half of the times in that subarray. A subarray is a contiguous non-empty sequence of elements within that array. We need to count the number of subarrays where the value target is the majority element. So basically The definition of the majority element we are given is that element that appears strictly more than half of the times in that subarray. So basically, so this is the definition of the majority element. So let's see the test cases. First, let's see the constraints. The constraints are size of nums is given till 1000. So that means the expected time complexity must be O of n square or O of n square log n. So let's see the test cases now. So the first test case is 1, 2, 2, 3, and we are given the target as 2. So basically, let's count the number of subarrays where the half of more than half of the elements are equal to 2. So this is one subarray, this is one subarray, and this is one subarray. In this subarray 1, 2, 2, 3, basically 2 is equal to the half of the length. So this is not a valid subarray where 2 is the majority element. So only these three subarrays, basically 2, 2, 3, 2, and 2, and 2, 2. So these four subarrays actually, sorry. And we cannot take this one because here number of 2's is equal to 2, which is equal to 4 by 2. So not the majority element. Here 2 is the majority element, here also, and here also. So answer will be 4 for this test case. 5, 2, 2. Okay, I missed one. This also. 5. 1, 2, 2. The next test case is 1, 1, 1, 1. Here all the subarrays will be having 1 as the majority element. 1, 1, 1, 1 with target 1. So the total number of subarrays here would be simply 4 plus 3 plus 2 plus 1. Or you can say 4 into 5 upon 2. 10. So the answer for this test case is 10. And the next test case, since there is no target element present in the array, so therefore there cannot be any subarray which has target as the maximum element. So the answer will be 0 for this test case. So basically, one observation that you can make is every number other than the target number has the same significance. Basically, every number other than the target number can be treated as a non-target number. Basically, we can visualize this array as non-target, target, target, and non-target, and still we will get the correct answer: 1, 2, 3, and 4 subarrays. So basically, 1 and 3 are they kind of have the same meaning in this question. So this is a pretty good start point. So now we have two types of elements, non-target and target, and we need to count the subarrays where the number of targets is more than half of the length of that subarray. Count of subarrays where number of targets is greater than equal to, greater than, actually strictly greater than length by 2. So basically we can say that 2 into number of target is greater than length, right? And we also know that since now we have only two types of element present, so number of target plus number of non-target is equal to length. So we can put this here and you will get the equation 2 into number of target is greater than number of target plus number of non-target. So we cancel this out. Hence we find this equation, number of target is greater than number of non-target. So we have now formulated a new problem which is identical to our original problem. We need to count subarrays with this condition now. Or we can say that number of target minus number of non-target is greater than 0, right? So what we can do now is to visualize this statement better mathematically, what we can do is we had our original array looking like this, right? NT, TT, NT. So NT, T, T, NT. To better visualize this condition in our problem, what we can do is we can replace the NT by -1 and T by +1. You guys will realize in a minute why. So basically this array will look like 1, -1, 1, 1 and -1. Now basically number of T minus number of NT would just be the prefix, just be the sum of subarray, sum of that subarray. So basically we have now formulated the problem that count subarrays with some positive. Since number of T minus number of NT would just be the sum of that subarray. Let's look at this subarray. So here we have 2, 1 and 1 minus 1. Sum of this subarray would be 1 plus 1, 2 minus 1, 1. And if we see that number of T minus NT is also equal to 1. So these two things are identical. So we need to count the subarrays with some positive. Now how can we count the subarrays with some positive? Here, so basically naively we can do this in 3 for loops. For I equal to 0, I less than n, I plus plus. And we can have another for loop, j equal to I, j less than n, j plus plus. These two for loops will denote the start and end of the subarray. And then we can run another for loop, k equal to I till k less than equal to j, k plus plus. And sum plus equal to, we can define a sum here, sum equal to 0, sum plus equal to nums of k. And after this for loop, if sum greater than 0, then the count of answer plus plus. So basically we can do this in n cube naively, but we can use a pretty common trick of prefix sums to do this for loop in O of 1. This whole thing in O of 1. So how can we do that? So we'll calculate a data structure known as prefix sum, where prefix sum of I will store the sum of nums j equal to 0, j equal to 1 till I, or 0 till I minus 1 in 0 base index. I have taken 0 base, so let's just take that also here. 0 till I minus 1. Actually, let's just take I, 0 till I. So this is prefix sum of I. And how do we calculate this? Naively calculating this will take O of n for calculating each index. So we use this prefix sum of I is nothing but prefix sum of till I minus 1 plus nums of I. So we can calculate values of prefix sum using this iteration, using this recurrence relation. So in O of n, we will be able to calculate the prefix sum. And then what we can do is, this is basically the sum of elements from I till j index, right? So this will be nothing but prefix sum j minus prefix sum I. So what this gives us is the sum of some variable t equal to I plus 1 till j of nums, right? So basically, since we need from I till j, here we have I plus 1 till j, because this was from j, from 1 to j, sorry, from 0 to j, and this was from 0 to I. So we have remaining elements from I plus 1 till j. So what we can do is, we can add another plus nums of I. So this will give us the value of this for loop, which is nothing but sum, and we can check if sum is greater than 0, then we can just increase our answer. So now we will only have 2 for loops and another for loop for pre-computing the prefix sum. So now the solution will be O of n square, and I'll show you guys the code. So basically, we declare another array V with the same size. What? Okay, so we we make another array V, where we, if nums of I is target, we set V of I as 1, else we set V of I as minus 1, and then we take the prefix sum, which is PS. So PS of I is equal to PS of I minus 1 plus VI, and PS of 0 will be declared as V of 0 because of this. And then we have these two for loops for left and right of the subarray, and then sum would be nothing but prefix sum till right minus prefix sum till left plus V of L, and then if sum is greater than 0, answer plus plus and return answer. One mistake that I made was, here we have nums of I, basically not the actual original nums of I, but the plus 1 and minus 1 nums of I. So this was the solution for problem B. If you guys have any doubts, you can ask. Okay, so let's move on to the next problem. Just a second, guys. So longest non-decreasing subarray after replacing at most one element. So you are given an integer array nums, and you are allowed to replace at most one element in the array with any other integer value of your choice. Return the length of the longest non-decreasing subarray that can be obtained after performing at most one replacement. A subarray is a contiguous sequence of elements within an array. An array is said to be non-decreasing if each element is greater than or equal to its previous one. And the constraints are, length is till 1e5, and the numbers are from minus 1e9 till plus 1e9. So the expected time complexity would be O of n or O of n log n. So Problem C. Basically, what we need to do is we need to find longest non-decreasing. Non-decreasing is greater than equal to, sorry, less than equal to, and that can be obtained after performing at most one replacement. That can be obtained after performing at most one replacement. So basically, let's see the test case. So that 1 2 3 1 2, right? We have 1 2 3 1 and 2. So what we can do, we see that this is an increasing subarray forming 1 2 3, and since we can make one replacement, so we can just change this value to 4, and then we will have this increasing subarray, non-decreasing subarray actually, which is of length 4 and which will be the answer. So the answer for this would be 4. And the other test case we have, we don't really need to make any changes. So the answer is simply 5, since it is already, the holder is already non-decreasing. So since we don't have any more test cases, let's just take one of ours. Okay. So let's take 1, 2. Let's make some test cases and try to see what happens. 1, 2, 4, then 3, 5, 7. So initially, without making any changes in the array, so we will have these two non-decreasing subarrays, right? 3, 5, 7 and 1, 1, 2, 4. We will have these two non-decreasing subarrays. So, but it is given in the question that we can do one replacement, right? So let's say that we have an increasing subarray. Let's try to find out what change we are doing. We have an increasing subarray this, right? So is there any point in changing this value? Is there any point in changing this value? So we need to think about this. Is there any point in changing this value? 2. What does changing this value do? Basically, it would do nothing, as clearly the next element will be 4, which will be bigger than 2 even if we change it. And obviously, if we change it and make this 5, which is greater than 4, then we are basically that is bad for our solution. And if we make it smaller, like -1, then again it will be bad for our solution. And if we change it to something like 1 or 3, so again that won't make any difference, since every element before this one would have to be smaller than this one, and every element after this 4 would have to still be bigger than 4. So changing this 2 will not really make any difference. That is the point. Changing it does not make any difference. Right. So now we have two other elements left. So basically this the case of 2 would be identical for every element inside a subarray except the border elements. For every element inside this subarray except the border elements, changing those elements will not make any difference, right? So we'll have to focus on just changing 1 and 4. So obviously changing 1 doesn't do anything in this case, but still it would change the lower limit of this subarray, kind of the smaller value of this subarray. So it might affect the answer in other cases. But what happens if we change this 4? So obviously we can see that if we change this 4,
for some values like 2 or 3, these two subarrays will connect, and this will become a non-decreasing subarray, which will be of length 6. So that is beneficial for us. So what value will we change this value to? If we don't know what elements come after this, basically if we don't know about these elements, right? If we do not have the knowledge about these elements, what value will we change this 4 to? We can say that if we are changing this 4, we will change it to be equal to 2, which is the last element. Because if we change it to equal to 2, we will be holding this non-decreasing subarray, and we will be making this value as small as possible so that the further elements could be greater than this. So changing it to 2 would be beneficial for us, or there can be cases where we don't need this subarray to be actually non-decreasing, and we just need to start our new non-decreasing subarray from here. In that case, if we don't need to ensure that this is greater than this, then we can simply change it to -1e9. So basically, other than these two changes, we will never really require any other change. So I'll repeat my point once. So let's imagine that there is a element ai, and the element before that is ai minus 1. So our answer would be a subarray, right? Our answer would be a subarray. So there can be two types of subarray that could possibly be your answer. If we want our answer to be like this, then we obviously need to change this to -1e9. If we are changing this element, then we will change it to -1e9. But if we want our answer to look like this, then we will change this to ai minus 1. Other than these two changes, we will never really make any other kind of change. So basically, either we set this element equal to the last element, or we set this element equal to -1e9 as small as possible, so that we can just start counting elements from here. So this will be our first observation. We will only change our element to either be ai minus 1 or -1e9. Right. So now we have this observation that we will only change each element from ai minus 1 to or -1e9. And we can only make one change. And we know that we can only make one change. So again, now with this information, let's try to let's make a test case and try to solve it. Let's just take the last test case only. 1, 2, 4, 3, 5, 7. So we see that let's try to find the longest non-decreasing subarray that we can make starting from this index. Starting from here, let's try to see what the longest subarray we can make by changing at most one index. So we see that first element is 1, we take it, and then we see that the next element is greater than 1, right? So now we have two problems. One, if we take the first element as 1, then we see that the next element is 2. So what we can do is we can find the 2, 4, 3, 5, 7 max non-decreasing after making a change. Basically, we can calculate the maximum non-decreasing subarray after making a change in this array, and 1 plus that would be the answer for starting with 1, the subarray starting with 1. Basically, the answer for this would be 2, 4, and we can change this to be 4. So 2, 4, 4, 5, 7 would be the answer, right? So 5 length subarray. So we can make a 5 length subarray starting from 2. So starting from 1, we can make a 6 length subarray. Because any subarray that we can make with 2, we can just simply extend it by 1. So 1 plus maximum non-decreasing subarray after making a change in this array. Or the other thing we can do is 1 plus, let's just make the change in 2. Let's just make it 1, 4, 3, 5, 7. So max non-decreasing without making a change now in this array. So we took care of the case where we don't really change the next element. We took the case where we change the next element to the AI minus 1. And another case that we have is changing this element to minus 1e9. So in that case, again our answer would be 1 plus 2, 4, 3, 5, 7 and max non-decreasing without making a change again, since we already made the change. So we have these three cases coming out of our original problem. We have these three sub problems. So now you might ask me that this first case says that maximum non-decreasing subarray after making a change in this array, right? And we have the same array here, and we see that again we have the same condition, maximum non-decreasing, but now without making a change. So obviously with making a change, after making a change would be obviously greater than equal to this test case, right? But the thing is, that is because 2 was already greater than 1. What if we had 3 here? If we had 3 here, this basically this transition would not be possible. Since 3 is greater than 2, so we cannot extend any subarray starting with 2 by 3. So we have two choices now, either to make this 2 as 1 or to make this 3 as minus 1e9. So we have these two choices. So we need to take care of these three changes, where one is we make this element as minus 1e9. The second is we make this element as 1, or yes, we make this element as 1, and this one is we don't make any changes. So we can see again, now we have this problem, and we will have again sub problems for this problem. So we can see a DP solution being formed. So what we need to do is, what things we need to store in the state. First of all, we need the I index, basically for what array we are calculating. Since we need for 0 to n, we need to calculate answers for 1 to n, right? So let's just store that first parameter of the state as I, which denotes that we are calculating for the array I till n. Now we need two more things, right? First of all, we need that we might have changed this element, right? We might have changed this element. It could have become either 2 or it could have become 1. So we need to store the information that have we changed the first element of this subarray. So we need to store that information as well. So for that, we can take another variable type, which will tell us if the current variable is the current index number has been changed or not. Also, we need to store another information. Do we need to find the answer without making a change or after making a change? So can we already made a change, or do we have still the option to make a change in the array? So we need to store that as well. Done. So basically for type, if type is equal to 1, then that means v of I has been changed to v of I minus 1. Or if type is equal to 0, then that means v of I is not changed. And for done, if done is 1, we have already made we need to, without making a change actually, without change, with a change, and 0 with a change. So now let's write the transitions. So for dp I comma type comma done. So first, by using the type, let's find out what is the first element of the current state. So val is equal to v of I, and val is equal to basically v of I if type is 0 and v of I minus 1 if type is 1. So now we know the first element of our array. So the one transition that we can always make would be dp of I plus 1. Not always actually. If v of I plus 1 is greater than equal to val, so that means the next element is simply greater than equal to this element. So there is one thing that we can do is we don't have to make any changes. We can just calculate the answer for 1 plus dp I plus 1, and then type will be changed to 0 since we are not changing the I plus 1th element, and done will be as whatever came down. So if it was 0 earlier, again still it will be 0. The next thing we can do is we can change the next element. So this will be only possible if done is equal to 0. So if done is equal to 0, that means that we need to find the answer after making a change. So we can it is possible that we are making the change somewhere further. So that will be handled in this case, since we are not making a change here and we are doing the changes further. Else we can make the change here only. So what we will do is 1 plus dp I plus 1 comma, now our I plus 1 would be equal to v of I, right? Because we are making a change, and we saw that the only two type of change would be that we will set ai to ai minus 1 or minus 1e9. So here we will be setting vi plus 1 to vi. So we will pass on the type as 1 and done also as 1. So these two cases will be for setting the value as ai minus 1. Now what happens when we set the value of some element as minus 1e9? It is simple. Basically the answer would just be 1 plus dp of I plus 1 comma 0 comma 1, which means that we can just find the answer from the next index without making a change. So if we have some array like this and the first element is 5, then we have 3, 4, 5, 6. So we can just make this element as 1e9 and find the answer for 3, 4, 5, 6 without changing any number. So this would be just 1 plus dp I plus 1, and no changes in the first element, and we cannot make any change in the array as well. So we don't need to include this in the transition. We can just calculate this case separately using this state. So these are the transition that we will be using for our dp, and simply the value of this state would be maximum of these two, and the base case would be if I is equal to n, then we can return 0. And so that's that. So now we can use this state to calculate what is the best answer we can get. So the best answer we can get would be simply for I equal to 0, I less than n, I plus plus, we can calculate the longest substring starting from each index and take the maximum of that. So maximum of dp I comma, not making a change, current element is not changed and we can make a change, this and 1 plus current element is not changed and this. So basically this is nothing but changing the ith element to 1e9 minus 1e9, and this is the simple case of where we find the answer for where the first element is not changed and we can make a change. So nothing that. So maximum, and we need to maintain an answer will be nothing but let's just store this value in temp, and answer would be maximum of answer comma temp. So this will, for each index I, we will find the longest substring starting from I, and then we can take maximum of all those to find the answer and we can return the answer. So the time complexity of this would be the number of states, since there are n into 2 into 2, which is 4n, and the number of transition per state is at max 2. So O of 8n, which is O of n only. So the time complexity would be O of n. Time complexity of dp is number of states into number of transitions per state. So I'll show you guys the code. So if I is greater than equal to n, then return 0. This is for memoization. Then we find out the value of val. So val is basically nums of I, and if type is equal to 1, therefore this variable, if this variable is 1, that means that the current number was made equal to the last number. So current number val would be changed to nums of I minus 1. Else, and if I is equal to 0, we can just consider that nums of minus 1 is minus 1e9, because that is the smallest number. So we can just consider nums of minus 1 as that. And here we have that condition, if nums of I plus 1 is greater than equal to val. So basically vi plus 1 is greater than equal to val, then answer would be 1 plus dp I plus 1 0 done nums 1 plus dp I plus 1 comma 0 comma done, 1 plus dp I plus 1 comma 0 comma done. And if done is equal to 0, answer would be max of answer comma 1 plus dp I plus 1 1 1 I plus 1 1 1. And then to calculate the final answer, we can take max of temp as max of I 0 0 and I plus 1 0 1 1 plus. So I 0 0 and 1 plus I plus 1 0 1, and answer is maximum of answer comma temp and return answer. So did you guys understand this? If you guys have any doubts, you can ask. It's a simple prefix suffix question. You are making it a more complex. I just came up with this solution. So bro, can you explain once more how you identify DP approach? Basically, I was trying to calculate the longest substring starting from each index. So let's say that we are trying to find the longest substring starting from this index, right? So what will happen? If we are finding longest substring starting from this index, we know that since here is 1 and here is 2, we can just find the longest substring starting from this index and add 1 to that, and that would be the answer from this index. We can see that. So we see that sub problems are being formed. Basically, if we solve for this sub problem, we can find the answer for this problem. So using that strategy, we can make use of DP here. Solved using prefix suffix, tried DP approach but could not build logic for DP. So let's move on to the next problem. So we have count subarrays with majority element 2. Here this problem is the same as the second problem, count subarrays with majority element 1. But the only difference here is that the length of the nums array is now 1e5. So I'll just go through the second problem solution, as we will just build upon that. So the second problem solution, I won't explain it fully. I'll just tell the final approach. So basically we replaced every target element with 1 and every non-target element with -1. And then we needed to count the subarrays with sum as positive. So we brute force then for all the subarrays. We found the subarray sum using prefix sum in O of 1, and then checked if the sum came out to be 0 and added that. So maintained the count for this number of subarrays, and that was the solution for this problem. So now since we have 1e5, we won't be able to run those two for loops also, right? Problem D. So basically what we were doing is prefix of R minus prefix of L plus nums of L. Basically this nums is that -1 or +1 array, not the original nums. -1 +1 array, -1 for not target and +1 for target elements. So we were counting pairs L comma R for which this is positive. We were doing this. So this equation is we can do this prefix of R minus prefix of L minus 1 greater than 0. So we can do this. So now previously we were just able to run 2 for loops, but now since the constraints are till 1e5, we won't be able to take 2 for loops. So let's try to do it in one for loop. So obviously one for loop we can run for R. We can just run for R equal to 0, R less than, and R plus plus. So then for each of these R, we will need to calculate number of L such that prefix of R is greater than prefix of L minus 1. Right? We need to calculate the number of prefix of L minus 1 which are smaller than prefix of R, where L belongs to 0 to R. So L minus 1 will belong to 0 till R minus 1, or minus 1 basically does not really exist, or we can just take it for now. So minus 1 to R minus 1 actually, and we can just use this prefix of -1 is nothing but 0, because we don't have any elements in -1, right? So that would be just 0 prefix of -1. So L minus 1 will belongs to -1 to R minus 1. So so we need to count number of k such that k belongs to the range -1 to R minus 1, and prefix of k is less than prefix of R. If we are able to do this for each R, if we can do this for each R, then in time complexity less than O of log n, then we can just add the value and we will get the answer. right? So what will be the naive approach for this? Let's say that we are not currently focusing on calculating this in O of n log n. So let's just try to implement this naively and then optimize it. So what will happen if we try to implement it naively? So what we can do is we can just run a for loop r equal to 0 and r less than n and r plus plus. And what we can do is we can maintain a vector which will store the previous values. And for each r, this vector will basically contain the uh, prefix of k for -1 till r minus 1. So what we can do for auto I in the previous values, we can just check if the I is less than prefix of r, then simply count plus plus. So using this for loop, we will be able to calculate in all the previous prefix sums how many were less than prefix r, and at the end of the iteration we can add dot pushback. We can add the value of prefix r to the previous vector, and initially the previous vector will contain 0, which is prefix of -1, prefix of -1. So this, and at the end of iteration we will just add the prefix r in the previous vector, so that our previous vector will contain all the prefix sums before that. And using this for loop we will calculate the number of prefix sums before r that are less than prefix r. So now we need to optimize this for loop. So basically what we are doing is we are having several, let's say, values in sorted order. Let's say this is some -7, -6, 0, 1, 3, 4, 5. So if prefix r came out to be 3, then we just need to add the, sorry, let's just take an array 0, 1, 2, 3, 4. Actually from 1 let's take it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Okay, so what does this array? Let's make this array store the frequency of number I in vector previous is nothing but is a of I. So basically if our previous looked like this 1, 1, 2, 0, minus and 3, so this will be nothing but the frequencies of each element. So 1 occurred 2 times, 2 occurred 1 time, and let's just believe that previous only has positive elements. That will make our life easier for now. So this and this, right? So let's imagine that previous looked like this, so this array would look like this, right? And then we need to count the number of elements less than prefix r in previous. So let's say that prefix of r came out to be 2. So naively we were checking every element in previous, right? And we also know that this previous, although this I have written a sorted array, but this previous will not be sorted because we are pushing elements in it which are not necessarily of the sorted order. So this previous would not be sorted. So we cannot take stuff like lower bound and something. So let's say that prefix of r was 2. So instead of counting in this, we know that we just need to take prefix sum of all the elements before 2 in this array. In this array, the prefix sum of elements, the prefix sum till index prefix of r minus 1. So basically nothing but let's denote the prefix sum of this array as p. So p of prefix of r minus 1 will be the will be this value. So again, to maintain this array and to calculate the prefix sum, we have a data structure known as BIT, binary index tree, or we can use segment tree and stuff also, but I'll just show binary index tree. So those who don't know about binary index tree, they can go and check this out. It is very frequently used in DSA or CP contests. So binary index tree, what this does is it allows us to make updates on any index and query the prefix sum after updates in OAuth login. So basically we will be using a simple point update range query data structure. In both of the operations are in login. So we will be updating a point and we will be querying for a range. So what does this mean in our context? Nothing but this for loop will now look like this. So we have for r equal to 0, r less than n, r plus plus. What we can do is simply now this whole for loop would be nothing but query of prefix r minus 1, and after we query we can just add this to our answer. And what we can do is point update, since we now need to increase the value of prefix r by 1 in the data structure, so we can do update prefix of r by 1. Right, so this is nothing but pushing back prefix of r in the previous vector. So these two things will give us the answer. But the problem, we have another problem. This data structure can be applied to positive numbers, positive indexes. Basically, the value of our prefix could be negative also. So we don't really have a negative index, right? We don't have a negative index. So how we will update the value at a negative index? So what we can do is we can use another pretty common concept where problems in which comes handy in problems like these, where we need to handle negative indexes or such. So we have something known as coordinate compression. So what we can do, since we know that our prefix array will have n values, right? Because we are taking a prefix sum of n length array, so it will have n values at n values. So we can sort these values and map them to 1, 2, 3 and so on. So what does this mean? Let's say initially our prefix array looked like -1 after sorting -1, 0, 1, 2, 3 and -2, let's say. So what we can do is we can consider -2 as 1 and -1 as 2, as 0 as 3, this 4, this 5, this 6. So if we use this mapping, then the relative order of the elements will not change, and each of the element will now have a positive value that indicates that corresponds to that element. So we can make the prefix array and we can create another array that is the sorted of prefix array, and we can map each of the elements of the prefix array to 1 2 3 4 5 6 and create a map of it, which will be named as get index. So now we will just change this to answer plus equal to query of get index of prefix of r, and we need every value less than prefix of r. For before that we were doing -1 for it, so we will just do get index -1. Get index of so get index just is just the index of prefix of r. And for also update, we will just update the index by value 1. So let's just index, and index is nothing but the mapping of prefix of r. So this logic we can use to map all the different elements in sort to 1 2 3 4 5 6, which will be used as indexes to store the frequencies. So here we can use this concept to calculate this in O of log n. So overall solution would be O of n log n time complexity. I'll show you guys the code. So basically this much is same. We are just calculating the prefix sum and replacing all the target elements with 1, non-target element with -1. So now we also have another prefix, which is prefix of -1, right? I told you prefix of -1, which is 0. So we add the 0 also in our list of prefixes, and then what we do, we sort the prefixes and we erase all the unique from the prefixes. So after sorting and erasing all the unique, we are now left with all the unique values in prefix sums in sorted order, and we can just create a map and map them to 1 2 3 4 5 6 and so on. Now this bit is for binary index tree, so we can just get the index of the current value in prefix, and then answer plus equal to sum is nothing but a function that gives the sum till current index, prefix sum till current index. So sum till index -1, and after the iteration we will update index with 1. So updating just adds 1 to the index. So, and these two functions are for binary index tree. You can read about that or using at cplgo or anywhere. Once you learn about that, you will understand these two functions. Rest, you can still use these two functions as a black box and just use the sum and update function. Sum will just give the sum till this index, and update will add 1 to the value at this index. So this was the code. I hope you guys understood. So if you guys have any doubts, you can ask. Okay, so I don't think you guys have any doubts, so I'll end the discussion. Thank you.